Today we're going to look at graphing functions, and not just a particular type of functions, but understanding that the transformation on functions, regardless of whether it's an absolute value or an exponential, it all works the same. In fact, this is the notation that we start to use where you see a little f here. All that means is I'm going to take my function, and that function might be an absolute value, might be a squared, quadratic, might be cubic, square root, who knows, but it's just some type of function right here. You see parentheses, but those might be absolute value, or it might be a square root. When you look at your function, this a value that's in front of whatever grouping symbols might be there, that affects your graph vertically, and it is a vertical stretch or maybe a shrink, or sometimes we use the word compression. The other thing that a value can do is it can cause your graph to reflect over the x-axis. The h value in this function, so that's whatever is inside of the parentheses, will always move your graph right or left. Because it's in grouping symbols, you'll always go the opposite direction. If you see a minus sign, it means go right. If you see a plus sign, it means go left. It's the opposite of what you would think. The k value is the value that's added out at the end, and it's always going to move your graph up and down, and then you do whatever it says. If it's a plus, you're going up. What we're going to do today is take all of those functions that we learned in our toolkit and start moving them around and giving them some sort of a transformation to look at. Let's start with an absolute value function. For this transformation to work, you always have to go back and remember the parent graph. In this case, the parent graph is the absolute value of x. That's what your y value is. It's the absolute value of x. And remember what the table would look like. You're going to go over 1, up 1, over 2, up 2, over 3, up 3. That's the rate of change for it. Now we know that it should look like a V, and so I could put in a whole bunch of numbers, but my goal is to probably avoid having to do this every single time and just remember what it looks like. But you can always go back to a table if you've forgotten. Looking at the function, I'm going to have a vertical stretch of 3. I think of this as my y value is 3 times whatever the function used to be, which means I'm going to take all of these y values and I'm going to have to take them times 3. That's going to be the shape of my graph. In addition to changing the shape of it, I know that it's going to have to go right 2 and down 5. And that takes the vertex of that V shape, and that's really what I'm going to start with. I'm going to go right 2 and down 5. This is going to be my starting point. That's the vertex of that V. And then whereas I would normally go 1 over 1 and up 1, I'm going to have to go over 1 and up 3, because I'm taking it times 3. Over 2 and up 6. Over 3 up 9. That'll tell me my shape. Let's go over to the graph and do it. From that vertex, over 1, up 3. Put in your matching point. Over 2, up, used to be 2, now it's going to be up 6. Over 3, up, not 3, but 3 times that, so up 9. That should be enough to get a nice graph. This is a nice V shape. Keep it linear looking. Make it pointy at the end. And there's our graph. Let's try a quadratic. This has a different table. The table for a quadratic is an f of x equals x squared. When we did that table, it was a 1, 1, 2, 4, 3, 9. If you look at this function, it looks like our y value is half of what it normally would be. And then this is going to be our shifting of our vertex. I'm going to go one more ordered pair so you can see this better. And then again, you're going to be taking all your y values and you're going to be going half of what they used to be. Let's start by graphing the vertex, right 2, down 4. And from that vertex, I'm going to go over 1, and it used to be up 1, now it's going to be up a half. Well, that's kind of hard. I'm going to probably sketch that, and it's not going to be very good, but right there is my up a half. I can kind of custom pick. I don't need to plot all of these. Let's pick the ones that are going to come out nice. If I have to take it times 1/2, let's pick the evens. I'm going to bypass this one. Over 2, not up 4, but up half of that. And this is always from your vertex, so over 2, up 2. Over 4, not up 16, but up 8. And that's probably enough. I'm going to go ahead and sketch my parabola then. Oh, I missed my points. I'm sorry. Not very neat. Kind of hard with my stylus. That's my excuse. Let's try it with a cubic. All of these are straight off your toolkit. And in a perfect world, you know your table from your toolkit, but I'm always going to write it here for you. 1 and then a 1 cubed. 2, 8, 3, 27. But all of these y values are going to be multiplied by a -2. The negative is going to flip my cubic upside down. Remember that a cubic looks something like this. Now it's going to start high and go this way. Let's go plot that key point. It's going to go right 4 and down 1. That's my new, it's not really a vertex, but my new key point that I shift, and then from there, that used to be at the origin, now I'm going to go back to my table and over 1, down 2. Over 2, down, down 16. That's way, way, way off my graph. So keep that in mind. If I'm way down here, this is going to get very steep very quickly. Let's put our other points on the other side. You're going to go left 1 and up 2. Or left 2 and up 16. Way, way off the graph. So let's bring this down. Put a little wave in there, and keep on going. All right, seem easy enough? This one is a rational function. Recall that rational functions look like this, and they have that's the hyperbola thing. What they have are asymptotes right here on your axes. You have 2 asymptotes. Those asymptotes kind of intersect at the origin, and so that spot at the origin is what I'm going to be shifting. The x minus 3, this is my left and right movement because it's tucked in here with the x, and I put parentheses around it. Though sometimes you don't see those parentheses there, you have to understand that that's grouped together. I will go the opposite. I'm going to end up going right 3, and this is going to take me up 2. It takes this intersection of my asymptotes and basically is just shifting my asymptotes. This one goes right. This vertical asymptote is going to go right 3. So let's put that in there. And your horizontal asymptote is going to go up 2. And I'm just going to slip in the hyperbola graph. If by chance this was a negative, or sometimes it's negative out in front, that's going to reflect your graph and make your hyperbola go in the opposite corners if it were negative. This one's not, so I'm going to keep it in the upper right and lower left. And I don't get picky about ordered pairs on this. I just want it located correctly, and I want you approaching your asymptotes. That's kind of all we have that's in that form. I wanted to review real quick a couple functions that you would have graphed in college algebra, and perhaps you did that big old bounce cut packet. I wanted to refresh your memory on that. If you see a rational function that's just written as one big fraction and doesn't have like the plus k out to the side, but it has x's on the numerator and in the denominator, if that's the case, it graphs a little bit differently. There's a little bit more action going on in these graphs. The numerator of these will always tell you where your zeros are going to fall. The numerator gives you your zeros. Your denominator is going to tell you where basically it's what x cannot be. Remember, you don't want 0 in the denominator, which is going to give you your vertical asymptotes. Let's start with that then. In this example, I have a 0 or an x-intercept at 0. I'm going to have vertical asymptotes at -3 and at 4. And I remember I called it the bounce cut packet. Anything, let's start with on the numerator, the zeros. Recall that if you have an odd power, which in this one I do because it's an x to the first power, that's going to be a cut. If it was an x squared, that'd be an even power and it'd be a bounce. In your denominator, if your value is to the first power, or is to an odd power, which both of these are to the first power, if they're to an odd power, those are going to be flips, so my graph is going to flip. If they were squared, or to the fourth, if they had even powers on them, they would be no flips. Alright, I've got that sketched in there. The next thing that you have to do is you have to figure out what your end behavior is. Your end behavior, basically you're counting up, forget all the numbers in it, and just look what's going on with your variable. How many x's do you have on top? Just the one. How many variables do you have on the bottom? Well, I'd have an x term times another x term, that'd be an x squared. That would simplify to a 1 over x. If I have a 1 over x, think about what that looks like as far as on the ends. We call that end behavior. Well, that's a parent graph. It's the rational parent graph. And recall that it basically, well, let me undo that real quick. Just very vaguely recall that it looks like this. We just did one of these, right? That's what it looks like. All I'm interested in is the end behavior. This part right here on the very end looks like it is approaching the x-axis from the underneath side. And here it's approaching the x-axis above. That's the end. I don't care about all the middle stuff. Who knows what, I got all kinds of fancy stuff going on the middle. All I'm looking at is making sure that the ends look like that. Well, let's start graphing it and see what happens. Looks like it's supposed to be underneath here, and it starts off and it looks like this, but then I come across an asymptote. I don't have any zeros up here, so I can't bring this thing up. I've got to go down. I come across this asymptote and it's a flip, which means as you are approaching this, you are headed downward and you're underneath the x-axis. I'm going to flip and come above the x-axis, and I'm going to be way up here as I'm approaching that. And then it comes down, and the next thing I come across is a x-intercept, so I'm going to cut through that x-intercept. And then the next thing I have is an asymptote that I have to go approach, so it goes on down. This asymptote is a flip, so since I'm way low, I'm going to come way high and come up here. And now I don't have any more x-intercepts, which means I'm ready to look at my end behavior. I want to be approaching the x-axis above it, so I'm just going to stretch this guy out and go approach. That's what that graph would look like. three main things that I'm wanting you to recall from that is, remember that your numerator gives you your zeros, your denominator will always tell you your vertical asymptotes, and you can kind of determine what your end behavior is by ignoring all the numbers and just looking at how many x's you have in your numerator and denominator. Let's practice one more of these. I made it a little fancier this time. Let's start off and look at our numerator. Anything in the numerator that would create a 0 is an x-intercept. The 2 doesn't really do anything other than a vertical stretch because there's not a variable with it. And we kind of ignore anything on our y-axis. I'm not worried about the 2. The x plus 3 would get me a 0 right here at -3. And since it's to the third power, that's an odd, so it's going to cut. The next 0 would occur at 1, and it's to the first power, and since that's odd, that would be a cut. The denominator is going to tell you where your asymptotes are, your vertical asymptotes, which looks like I'm going to have one at -5. It is to the first power, which would make it a flip. And I have an asymptote at +3, again to the first power, again would be a flip. In behavior is a little fancier here. If you count up how many x's that you have in your numerator, you have this x, but it's being cubed, and then you have another x. You have a total of x to the 4th. In the denominator, you have an x times an x, that's going to be an x squared. That would simplify to x squared. An x squared looks like a parabola. It would start up high, come down. It's going to do all kinds of stuff because I've got a fancier equation than just a basic parabola, but the ends should look like a parabola. Ignore this and just pick out the ends and make sure your ends look like that. Coming down to this graph, then, I know that my end has to be way up here and look like a parabola. And then as I'm coming down, I have to see what I come across. And I don't have any x-intercepts. The first thing I come across is an asymptote. I cannot go down because I can't cross the x-axis, which means I must have to come up. Kind of looks like a little parabola there. And then since I'm headed way up, and then it's a flip, I'm going to have to jump and go way down. Come up, the next thing I come across is an x-intercept, and it's a cut, so I'm going to cut. And then the next thing I'm going to come across is another cut, so I must have to turn around. And then I come across this asymptote, let's go approach it. Obviously this is kind of, this would have a prettier curve to it and such. I'm just trying to go slowly so you see the thinking process. That asymptote that I've approached is a flip, and since I'm way low, I'm going to come way high. And then I have to decide what to do. I can't cross the x-axis. There's no x-intercepts. I know that my end behavior is supposed to end up going up like a parabola, so let's go do it. And that's your graph for that. All right, lots of different graphing that just by knowing some basic rules, you could graph just about any function. Hope this helps.